tomorrow. So here we go.
All right, so on 4A, when we added this up, what do we get before we had to round?
So let me work with my names here. What do we get before? EJ. 435.2 milliliters, right? All right, so then you went and you said, okay, this is my process is this is an addition problem. Which type of rule do I use? I count the digits after the decimal. So counting the digits after the decimal, I have one digit, no digits. So then you guys said this was going to have to round to what? 435 milliliters, because that too does not influence the 5 to get rounded up. It just keeps it the same. So whenever you're walking through it, always try just do your calculation first, then say which rule is it. This happened to be the addition. Let's go down to D. So Lindsay, what'd you get before you rounded?
7.692.
7.692, and that would be kilograms, right? Okay, so then you counted, or first you saw there were three, or this was an addition question, so 3 digits after the decimal versus 2 digits after the decimal. So then what do you have to do? So round to some number with only 2 places after the decimal. So then that 2 gets knocked out, and it doesn't cause the 9 to round up. So it's going to stay 7.69 kilograms. So far, so good? Okay. Next one is a division. So 120 divided by 8.56. Robbie, what'd you get whenever you just did the simple math first? For J.
Right before I rounded.
Okay, so whenever you have, so just for your own sake, whenever you could do your work like this, I mean, you're putting in your calculator, I know that. So if you could show you that first number before you round, it'll help you realize how you got where you're going, okay? Margaret, tell me what you got. 0.187. That's a 0. Okay. And that's going to be kilometers what? It's divided, right? Okay. So kilometers squared divided by kilometers, you subtract the exponent, so you just get kilometers, right? All right, so how many, or what was your next thought? I got my final answer. Not really, but I got an answer. What do I need to do now? I count sig figs, because this is a multiplication division problem. Sig figs in the first one is what? 2. Sig figs in this one? 3. Weakest link wins, right? So 2 sig figs are what's going to control my final answer. That's pretty easy. You record the first 2, and then you double check. Does that 0 influence the 4? No, so keep it as it is, 14 kilometers. All right, last one. That number divided by that number. What'd you get, Chloe?
I don't have my before number either, but I can use that.
No, that's good. I got Caroline. Yeah.
0.028.
0.028. Is that what it was before rounding? Yeah. I need to double check. Yeah.
Yeah.
Okay. What's your unit?
Millimeters.
Just millimeters, because millimeters cubed divided by millimeters squared. All right. So then, how many? I'm sorry. Are we looking at sig figs or decimals? Sig figs, because this is a division problem, right? Anytime you're doing division or multiplication problems, you should be saying count sig figs. How many sig figs in the first big number? 4. How many sig figs in the second one? 3 sig figs. So how many, or how should I adjust this to make it look like it has 3 sig figs?
Wouldn't you put a 0 behind it?
Yes, because you need to ensure that once you start counting, right? Start at the 2 and then the 8. You need one more decimal or one more digit afterwards to ensure that it has 3 sig figs. So that would be the best answer. So as long as you're even comfortable with the fact that you should be always like having that last minute thought of like, oh, does that have the correct sig figs? That's what I'm looking for in our calculations. And you'll be showing that throughout your lab today. You'll be doing some math, right? You're showing me how you're calculating your density. And then through that calculation, you're always going to be ensuring those correct sig figs as you go. So the rounding one is always, I swear, it's always the one that people are like, I don't know why we're rounding this way. But I do think you're seeing that rounding is coming into play as we are doing or finalizing our calculations. So for this one, let's do 5 sig figs first, and then we'll put in scientific notation. Or that might kind of be the way we have to write it. So we have this large number, right? 5 sig figs would be what? first 5, right? 1, 2, 3, 4, 5. Well, I can't just write 23,465 because that wouldn't even be close to the true value. So I have to employ scientific notation because it helps me write the correct number with the correct sig figs. So scientific notation is just a tool to make sure we meet the criteria of 5 sig figs. So how would you write that? 2.3, 4, 6, 5. Now, is this 5 correct? Do we need to round it? No, is that 0, which is next, does not influence the 5, so we're good. So then times what? So we put an artificial decimal here, right? The true decimal is way over here. So 7, great. And then whatever the measurement is there. So that is 5 sig figs, and it's the same value here, just rounded. I like scientific notation because you can always see the sig figs right in the front of the number. All right, so any other random questions from problem set 3A that you were like, oh, I'm really not sure I got that right? Yeah.
Before C, like how would you put, would it be like centimeters? Like that was confusing.
So you use centimeters cubed divided by centimeters to the first. 3 minus 1 is centimeters squared. Yeah. Another one, raise your hand. Yeah.
Number, like part 1,
Oh, yeah, let's go over that real fast. All right, so here's with me. So never true, always true, or sometimes true. A, never. B,
always true.
sometimes. It's going to be large and small numbers, not just one or the other. So if you just want to put an X, I think it's really valuable for you to put a scratch through it so you know you got it wrong, right? Because then after when you get these things back when you're studying, only know these other things you got wrong, not everything, because you obviously knew it the first time. C. Always be confident. Even if you're wrong, be confident in being wrong, okay? D.
Sometimes.
Always. Between 1 and 10. Okay, that number in front. Always between 1 and 10. E. Never. F.
Always true.
Never true. Never true. I'm right. I just have notes to myself. I don't have the question right here in front of me. What is that one? What was that? F? Oh, let's not write F. Oh, no, yeah, it's 10 times smaller, not 100. 100 would be what? Centi. Okay. G? SI unit of volume is a derived unit from length. Sometimes, why? Well, and then, oh, I see what you're saying. Volume. What are multiple ways to express volume? What are all the units? Yeah. Hold on, sorry, my board is having a little freak out. So liters, milliliters, or centimeters cubed. Do you remember derived measurements are just when you have a calculated measurement. So like the centimeters cubed is centimeters times centimeters times centimeters. So that's a derived unit, whereas these are just like straight up units. They're not derived units. So that was one of those terms that you learned in your video. All right, next, or close to last, H. So G was sometimes, yes. H is what? Remember? So meters, liters, grams, degrees C, Kelvin. That's my alarm to take attendance. Okay, guys, I gotta take attendance in a second. Okay, I can see that some people might have said always, some people said sometimes, because there are lots and lots and lots of sig figs. SI units. And then so if you said always or sometimes, I would take it, because sometimes people have a prescribed chart in the textbook that are just the 6, but there are tons of SI units, so it's okay if you put sometimes. I. So the density of a substance decreases as its temperatures increase. So sometimes that's true. Sometimes things swell. What? I'll talk to you in a second. Okay. Sometimes that's true because as things swell, they take up more volume, so their mass is spread out more amongst more volume. And we're going to watch a little video on that today, okay? So some of this stuff is in your textbook, some of it's we're going to be covering in class. So last one, if you put sometimes true, we're good.
Okay, hold on to that for a minute, and then let's go ahead and watch this video on density. I'll come around and take it out from you guys, and then you guys should write down if you want to have a separate sheet of paper. I'll take more questions after I look at these. Separate sheet of paper. Maybe it's your notes from yesterday that you're tacking onto, but we're going to be writing down a couple of notes from this density video. Density video. Is everybody here? And then Elizabeth, you got the textbook behind you. Make sure you grab the one that's yours. And then Cameron, forgot your textbook yesterday. Make sure you grab it. Everybody's here. Okay. You do not have to bring your textbook every day. Some people left their textbooks in my room yesterday.
When do we need to bring them?
Probably never. I will let you know. It's once in a blue moon.
Okay.
Okay. All right, so these are 5 facts about density. I want you to write down the 5 facts about density. Pretty easy, right? I just took attendance, so I'm on a roll here. I also have to turn off Pandora.
Density facts. A can of Diet Cola will float, and a can of regular cola will sink when placed in water. You see, in the same amount of fluid ounces, there are more atoms in the can of regular cola. The main ingredients in cola are carbonated water and sugar. So each can has the same amount of water molecules, but in the same space, the regular cola has additional molecules from the sugar. Putting more atoms in the water forces the molecules to be more dense, making the cola sink. Hot air balloons fly because of density. Just like all matter, air is made up of atoms and molecules. When air inside the balloon is heated, it expands or gets bigger. So compared to the air around the balloon, the atoms inside have more room to move around and as a result are not as tightly packed together.
Therefore, they are, say again? Less dense, right? They're not as tightly packed together, they're less dense, yes.
Wait, what was the first fact?
What was the first fact?
Cola doesn't, cola sinks, but Diet Cola doesn't.
Why does Diet Cola not?
Because it doesn't have enough, it doesn't have that many atoms in it.
So it doesn't have as much mass per its volume, right? So it's probably because it doesn't have that heavy sugar in it, whereas Diet Cola doesn't have the heavy sugar Coke or regular Cola does.
Wait, what's the second fact?
What's the second fact? I'll back it up a little bit. I'm picking up homework, so I'm listening and doing this with you guys. Okay.
Regular cola has additional molecules from the sugar. Putting more atoms in the water forces the molecules to be more dense, making the cola sink. Hot air balloons fly because of density. Just like all matter, air is made up of atoms and molecules. When air inside the balloon is heated, it expands or gets bigger. So compared to the air around the balloon, the atoms inside have more room to move around and as a result are not as tightly packed together. The air inside the balloon is less dense than the surrounding air, and the balloon becomes buoyant. When it's time to land, the pilot stops heating the air, and as it cools, it contracts to match the density of the surrounding air. The effects of gravity go to work and bring the balloon down to Earth. If an object is cut in half, its density remains the same. Take a look at a gold coin, made of neatly arranged gold atoms. When cut in half,
I know some people are carrying out their prom sets. What's the third fact? So if an object is cut in half, its density stays the same. And it's going to tell you that you can see the atoms here. The atoms themselves have mass, and they're going to be broken apart in half. Well, then also the volume, again, which is the space it takes up, is being cut in half. So all you're doing is pushing half of it that way, half of it this way. The density, the value of its density does stay the same.
the tightness of the atoms does not change. Whether you have a half of a coin or a complete gold coin, the density stays the same. The density of liquid water is 1. Objects with a density of less than 1 will float, and objects with a density greater than 1 will sink. Take a look at these three.
Let you guys write that down. I know he's talking fast here.
Can you replay it?
Hmm?
The same. The density of liquid water is 1. Objects with a density of less than 1 will float, and objects with a density greater than 1 will sink. Take a look at these three objects. All of them float, so their densities are less than 1. But if you take a closer look, you see that as density increases, more of the block is below the waterline. Scientists have figured out the density of a block converted to a percentage is equal to the amount below the waterline. For example, if 75% of a block is below the waterline, its density is 0.75. Ice floats because of density. When water freezes, it expands. Just like the expanding air in the hot air balloon, water molecules in expanding ice spread further apart. The atoms in ice are not as tightly packed together as they are in the liquid phase. If we observe an iceberg, notice about 92% of the iceberg is below the waterline. This means that the density of ice is 0.92. Density facts.
Okay, so now you kind of see on the particulate matter side of things what density is referring to. It's referring to the number of particles packed into a small, of a certain volume. I won't say a small space, but it's a space. So let's do a couple of density problems, and then we're going to get to our lab. What was the last one? Ice is less dense than water, liquid water, right? So this information here is their terms. You guys have seen these terms before. Who thinks that this is foreign to you? Mass is the amount of matter, in an object. Is that foreign? You kind of know that. And if you want to write down some of it, write down some of it. I'm not going to spend very long here because I want to practice with you, because some of the terms are things that you have prior knowledge of. So mass is going to be recorded in grams generally, grams or kilograms, and that is just the amount of matter. Weight, however, is what we take advantage of a lot of times in the lab, because it's referring to how gravity takes impact or takes effect on that matter. So generally, how do we mass something? Like, what kind of tool do we use? You with me, EJ? Thank you. Put it away. Okay, talk to me later about that, because I need to prove that. So what kind of device do we use to get mass? What's that tool called? Say it loud, I heard it. A scale, right? We have scales that we use at home. We have them in the labs as well. We're going to be using this today to get our masses. Now, my scales are haunted a little bit. You have to wait for them to settle and get the final value. The numbers fluctuate up and down. It's just because of vibrations in the room, because the vibrations cause the scale to kind of vibrate, I guess. So you just want to, if it's not steadying, just go 3, 2, 1, whatever number you see, record it, okay? FYI. All right, so mass is different than volume because this is the amount of matter, whereas volume is the amount of space that that particular object is taking up. And so when we pull these two together, we do start to be able to calculate density. So density is the ratio of mass to volume. So the ratio of mass to volume, maybe you've seen this triangle like this before. Have you guys ever used a triangle like this? What class? Science with density, I'm thinking earth science, right? So, but we don't necessarily need to know the triangle. We need to understand that density is simply the ratio of mass to volume. So what are the appropriate units for density? What's the appropriate unit for mass? Grams, right? Grams or kilograms. I'm going to stick with grams because that's what our scales do measure in. But there's many different ways to express volume. So what's one way to express volume? Yes? Cubic centimeters. And that's one that we will use frequently whenever we're using things like rectangular prisms. because that's going to be length times width times height, right? Volume of a cube or a rectangular prism. What's another way to express density? Grams per, what's another unit of volume? I heard liters. Give me the smaller version of that. Milliliters. A lot of times we're not, so air around us is going to be taking up tons of liters. But the equipment we're working with are probably graduated cylinders, right? And so those have little bitty measurements, milliliters on it. So these are the two that we will frequently use, and these are the two I expect you're going to be using in your lab. So make sure you put a big star by that, because that's the unit that's appropriate for density. So I want you to also note that when we're dealing with water, so if I had a cube of water, not a nice cube, okay, just like a cube of liquid water, if I measured it, 1 centimeter by 1 centimeter by 1 centimeter. That would be 1 centimeter cubed, right? Well, I could also throw that into a graduated cylinder, and it would take up exactly 1 milliliter. Anytime you are like trying to figure out how do I convert from centimeters cubed to milliliters, it's a 1-to-1 ratio. They are equivalent to each other. Therefore, that's why we can interchangeably use centimeters cubed and milliliter, because they are one and the same. So that's a really helpful point, because a lot of people, sometimes when you're doing conversions, you're like, how do I get from cubic centimeters to milliliters? This is it. Yes.
Is this for any other kind of measurement?
Any other kind of measurement you mean other than water?
Yeah.
We generally say it does apply to most things, because this is related to their amount of space, not their density. So if they can take up the same amount of space in a cube or in whatever the shape of a milliliter takes up, we say it's interchangeable. So not just water, but I'm using water right now because that's what we're going to be doing with water displacement in our lab. Other questions right now? Okay, so let's do a quick problem. Actually, let me come back to that because we already did that in the lab. If I have a rectangular solid A, and it says the mass is 152.2 grams, its length, width, and height are 3 centimeters. I'm sorry, its length and width are 3 centimeters. Its height is 2 centimeters. What's the formula for the density of the rectangular solid, and calculate it? So let's pause for a second. How many numbers are given to us? 3, right? Okay, so before we move on, let's think again. What's the formula for density? It's what? Mass over volume. Okay, so mass over volume. All right, so do we have the mass given to us? Yes, okay, that's good. We are easily taking this number, and that is the mass. That's it. 152.2 grams. Do we have the volume given to us? No. So, but we have step 4 volume, right? So how are we going to find volume? Okay, so length times width times height. So what's that? Well, can you tell me the math for it? 3 centimeters times 3 centimeters times 2 centimeters. So this kind of process should look familiar to you, right? Now, in your back of your mind, you're going, sig figs. Okay, so whenever you're showing work for problems like these, do not just plug in your calculator. This is a show your work class, because if not, I really won't be able to guide you to where you're going or see where you messed up. It's really imperative that you show me something so I can see where you're coming from. So whenever you do this, you said 3 times 3 is 9, times 2 is 18. I thought I heard 15 from some people, so this is 18 what? Centimeters cubed. Okay, so I want you to not round this yet, because this is not our final answer, right? It asks for density. So we're not going to round this yet, because we're going to plug it in here, and then we're going to think about our final answer in its appropriate sig fig. So this equals 18 centimeters cubed. Plug that in there, and somebody please calculate 152.2 divided by 18. 8.45. The whole 4-5 repeat, or just 5? The 5 is repeating. And then what would the units be there? Units? Right, since both of these units are are different, we have to keep them both, because neither of them cancel with each other. Grams per centimeter cubed. Okay, so if we're here so far, we're like, okay, final answer. Close, but not there yet. How many sig figs should this final answer down here have? 2. 3. It should have 1, because that's one sig fig. This should have one sig fig. Now, I'm not rounding this because that's not my true answer I'm looking for, but I'm thinking in the back of my head, this should really have one sig fig. That should. This has how many? Four sig figs. So now if I'm thinking 4 sig figs versus the should have 1 sig fig, which of these is controlling my final answer? The 1 sig fig. So this needs to be rounded to 1 sig fig, which would be just 8, right? Because you record the first number from the left side. So to our best judgment, we're saying that whatever this is, this rectangular solid, has a density of 8 grams per centimeter cubed. We do have to drop the last two numbers because we're following sig fig rules. So that's how we're starting to employ calculations and rounding, all in a new problem. Who followed most of that? 2 thumbs up. All right, cool. So we did centimeters cubed here, right? What's the other version of volume? Milliliters. And most of the time that's going to be through water displacement. Who's ever done water displacement in a graduated cylinder? Okay, so some of us are pros here, but whenever you do water displacement, you always fill up some water in your graduated cylinder. Don't leave it at 0. Don't leave it at 100, because if it's already at 100 and you drop a rock in there, what's going to happen? It's going to go higher to this non-graduated area, and you're going to be guessing, and that's not cool. So, put about halfway, drop your rock in. You can see that it raises a certain amount, but you can't see these, so we're going to read it here. So the mass of a rock is 45 grams. Important, right? We're going to need that. The volume of the rock is calculated by doing water displacement. The original water was at 60 milliliters. After putting the solid in the graduated cylinder, the water level rose to 75. So, guys, what's the volume of our rock? 15, because you said final 75 minus the 60, and you said that was 15 milliliters. How many sig figs should that final answer have?
2.
Okay, I tricked you.
1.
We're doing what?
Subtraction.
So are we talking about sig figs?
No.
So no decimal, so nothing after the decimal? So we're good, right? Okay, so just keep that as is. It's usually like a 3 or 4 second thought with yourself. And then we need to now find the density. How do I find density? How do I find density? So I hear mass divided by volume, and you said whatever what? 45 grams over 15 milliliters, and then that is? Okay, so if I wrote 3 grams per milliliter, would that be 100% right?
Yes.
No. Who said no? Go for it. Tell me what the correct answer would be.
Oh, never mind. I thought I was looking at the.
But you were right when you said that. Oh, the units are fine. Grams per milliliter. I want you to tell me why this 3 is not 100% correct. Go back, right? So this is a division problem, right? What should we be looking at? Decimals or sig figs? Okay, how many sig figs should we have?
2.
Okay, so correct it.
3.0.
3.0. Because we are super accurate. It's not just 3. It's 3.0. All right. Pull out a piece of paper for your density lab. All right, go ahead. Call this density lab. But purpose. Every single lab will have just a little bitty purpose statement. Sometimes, whenever you read it over to the lab, you're realizing that there's some goals and that there's an introduction, and you're like, okay, goals of this lab are blah, blah, blah. So, whenever you go back to your labs, you are going to be looking in the cabinet, and the cabinet has like a colorful notebook. That notebook has all the labs in the world for you, okay? This lab, density lab, it's titled Density Lab Inquiry. Who knows what inquiry means? Sometimes it means like question, right? Sometimes inquiry, when we're talking about it in a physical way of doing things, it means that it's not as guided. So you're going to think, come up with solutions to your own problems amongst collaborating with your peers, and then you're going to solve problems versus Emily going, do step 1, do step 2, do step 3, do step 4. So I'm not guiding you through the entire thing. It's your problem solving. So you're going to be given 7 to 8 items. Sometimes they're like little plastic frogs, paper clips, nuts and bolts, things like that. And you're going to have to use all the equipment at your disposal, which is underneath your lab cabinet and in your drawer,
to find the density of these things. So I said find density, but what do you mean? What do you know that actually means? With the equipment you have, you're going to find mass and volume, and then you're going to have to calculate your own density. I need to see all numerical numbers from measurements to calculations to correct sig figs and such. Whenever you get done finding the density of all of them, line them up in order from least to greatest density, and you're going to take a picture of it, and one person from your group, I don't need 3, okay? One person send that to me. And if we have time at the end, everyone's going to be graphing. I have graph paper for you. The results of your density lab to practice graphing. And I will kind of explain this more maybe towards the end of the lab, but you're going to be doing mass versus volume on a graphical chart here. And all you're going to do is make each object have its own line. So if there's 7 to 8 objects, you'll have 7 to 8 lines. And I'm going to show you how the slope plays into the density at the end. Yes, ma'am.
So I would write down the purpose.
Whenever you get back there and you read your introduction to the lab, you can kind of talk to your group mates and go, what do you think the purpose of this lab is? For this one, I can probably tell you, it's to practice using lab equipment appropriately, calculating with sig figs, and the density formula. Excuse me?
What's the purpose?
What did I just say?
Practice using lab.
What else? Sig figs and the calculating density. Okay, so sometimes it's just like skill practice, okay? So please have your closed-toe shoes on. When you're ready, please go to your lab station. Find the lab inquiry density, and it's the same lab group members you were with last lab. Okay? And you guys can modify the purpose. Not everybody's purpose is going to be exactly the same. It's up to your interpretation. This lab you do not need eyeglasswear for, okay? Just closed-toed shoes is fine. Yeah.
I feel like we're having to wear closed-toed shoes. I have shoes like down in the locker, but if you don't want me to go get those,
Go and grab them. Yeah, because I want to make sure everybody has their closed-toed shoes on. Take the monkey. Take this monkey and go down to the locker. Thanks. I'll try to check this during the class period, okay? I have something for you, hon. Hey, right now, hey guys, give me a quick eye check here. See my face? Can you see your face? Okay, this is the inquiry density lab, the one over here, and it says density of a solid inquiry. The title was a little different than what I said earlier. You'll see the necessary information, you'll see some questions. The analysis questions will get done after you get done what I had on the board, which was show your work density, organize them from least to greatest, and then email me. So you'll do the analysis that you can in class. We do have about 45 minutes left, maybe a little less. So you will divide and conquer. So if there are 3 people at your lab station and there are 6 or 7 objects in your basket, how many is each person doing? 2. You need to double check each other's work. Make sure you're working together still, but you do need to divvy up some of your tasks. Oh yeah, use that one.
I'm coming.